Hello everyone, welcome to the Isaacson session. My name is Chan Wan. I am a research engineer on the Isaacson team. My colleagues Renato and Hamad will join me later for various parts of the talk. Today we will talk about what Isaacson is all about, how you might start using it, and what's new and updated in our latest release. Isaacson is a robotic simulator application built on top of the Omniverse platform. To start, let's talk a little bit about what we want out of a robotic simulator. So building a robot is hard and expensive, and what a simulator ideally should allow us to do is to quickly, safely, and cheaply prototype robots and the environment that it's in. It should allow us to make mistakes that we can't afford to in the real world. It should also allow us to scale up our simulations so that we can collect a massive amount of data that's needed to train our AI algorithms. And it should also act as a visualizer for us humans so that we can see what the robot sees to anticipate its movements, so we can use it for planning and debugging and communicating purposes. Isaacson is NVIDIA's answer to this need. We are set out to build a robotic simulator that lets you build robots in environments as close to the real ones as possible by having realistic physics and realistic sensor outputs, as well as having the additional tools that makes these desired features easy to access. So Isaacson is built on top of Omniverse. We'll just have a very high-level summary of what Omniverse is. But if you're interested in learning more, there are many more talks that are dedicated to that topic in other GTC sessions. But on a high level, you can think of it as the Google Docs of design. The idea being, when you're using Google Docs, multiple people could be using different browsers on different OS sitting in different locations, but working and editing the same document in real time. In Google Docs, the platform is providing you with the word editing features, as well as making the syncing and integration smooth. Omniverse is kind of like that, but for design. So imagine you are developing a video game or an animated movie. You'll have people working on all parts of the project, and these people are from different studios using different software and probably sitting in different parts of the world. Omniverse is a platform that allows you to have a place where everyone can work together, connected to the same platform from whatever software they're using, and they can even have real-time interactions so that their edits and changes are instantaneously available to other team members. And Omniverse is behind the scenes providing a set of core technology that makes that possible, including the real-time ray tracing and path tracing rendering technology, the physics simulation based on PhysX, and conversion to and from different formats to USD. So there has been quite a few applications built on top of Omniverse. Here are just some examples, each aiming at a different specialty. So some are for game developers, some are for artists and architects, and Isaacson is built for roboticists and robotics researchers. What Isaacson is leveraging from Omniverse is its fast and photorealistic rendering capabilities, its flexible and versatile material assignment, the realistic physics, the Python C++ interfaces, which allows us to build customized extensions, and ability to run headless either locally or on the cloud, which is what makes it possible to scale up simulations. Omniverse also has this thing called a nucleus, which you can think of it as a library of assets and tools that you can borrow for your own needs. And we're also leveraging the ability to import files from different software and formats so that it makes it easy for you to import your existing setup. So here is an overview of Isaacson features. In terms of importing and editing, we are providing importers for Urdf and CAD. We also have a special importer for ShapeNet objects. ShapeNet is this library of annotated assets that are frequently used for robotic research. You can interface with a simulator via the GUI, as well as Python C++ scripting or Jupyter Notebook. In terms of our simulation capabilities, we can simulate a range of sensors such as camera, depth, LiDAR, ultrasound, IMU, and contact force. We also provide some basic tools in perception, motion generation, and navigation, so it's easier for users to build full systems, especially if you just want to focus on one part of the system and want the rest of things just work. For example, if you are working on task planning and you don't want to worry about finding your own inverse kinematics algorithms to run your robot, then we can provide that for you, as well as ground truth perception and segmentation data. You can obviously also connect up your own algorithms. You're not forced to use these built-in ones. We also have communication channels through ROS 1 and 2, as well as Isaac SDK, so you can connect up the simulator with the rest of your system. And we also provide tools that helps with collecting data for learning and training, namely a synthetic data generation toolset that makes domain randomization and data recording easy. So without further delay, let's open up Isaacson and see how you might start using it. Let's start with importing a robot using the Urdf importer. Urdf is a file format that is especially popular if you use ROS. Here I have a Urdf file for the Dingo robot from ClearPath. This was first converted from a Zacro file using a ROS command. And you can see that it has all the usual suspects of Urdf, such as material properties, local paths to mesh files, visual collision links, initial properties, joints. To import this, first you want to make sure that your ROS package path is set in your environmental variables before starting the simulator, so that you can find the package paths for the mesh files. And once the simulator is loaded, we can just open the Urdf importer under Isaac Utils. We will choose to merge the fixed joints, unfix the base since it's a mobile robot, and change the motor to velocity drive. And here it is. You can see that they have the real sense camera and validying sensor are both there. Let's add a ground beneath it and some lighting. And we can just go straight ahead and drive it around using velocity control. Here we go into the joint drive properties and set a velocity target for both wheels. And now the robot moves. So that's pretty straightforward. Most commercial robots have some version of Urdf, but if you happen to have built a robot from scratch, then we also have a step importer for you to import your robot straight from CAD. I will let the architect of that feature, Renato, to tell you all about it.
The CAD importer supports step and IGES exchange formats and imports the entire assembly structure, loading solids, surfaces, and composite parts. Importing a CAD file is easy. Search for your CAD file in the content browser, then right-click on it and select Convert to USD. We bring all information available when importing, such as the assembly structure, parts density, colors assigned to bodies and surfaces. However, these formats are unable to hold the kinematic structure from the assets, so some post-processing is required. To set up your robot, start by defining the rigid bodies on your asset. If you have your assembly structure already split in subassemblies by rigid body, this is easy. Select the subassembly level and then click on Add Rigid Body with Collider's preset. This will treat all objects inside as a single body and will add collision properties to all meshes. Once you're done setting up all rigid bodies, then it's time to set the joints. One recommendation to simplify this process is to keep assembly positions aligned with the joint's pose. This way, you can use that information to build kinematics of your robot. Click in Forward Kinematic Order on the bodies you want to assign the joints, and then click on the Create menu, Physics, Joints, and select the type of joint that you want. To set up the joint direction, click on the joint at the stage tree, and on the Properties pane, select the axis of the joint that will be actuated. And to actuate the joint, you must create a joint drive. If the joint is driven by a velocity target, set a value greater than 0 for dampening. But if it's a position target, then set the values for both damping and stiffness parameters. We can also import CAD documents directly from Onshape. It imports the same information that the CAD importer does, and it also does physics authoring based on made information present on the document. To import an asset, click on File, Import from Onshape, and search for the document that you want. By default, it will search only your documents, but you can also change the filter options to search for public documents. When you find the document that you were looking for, click on the title to expand it and show all available assemblies, or if it's a single assembly, double-click it and it will start importing the selected option. If you have the mate set up, the importer will automatically alter physics, with the joint positions and limits provided by the document. Once the document is imported, you can set up the joint drives for the given degrees of freedom. By default, the importer will assign a convex mesh simplification for all components on a rigid body. For complex assets, for example the Kaya robot, this becomes a performance bottleneck. To avoid that, you can alter your own set of colliders by using basic meshes and primitive shapes. Take the roller on the Omni wheel, for example. We can simplify this by using 2 cylinders on the bigger radius and on the smaller radius. After adding the collision API, check the custom geometry box. This will tell the collider solver to use the numeric function of the geometry for a smoother surface. Once you're done with the colliders, you can select them and then go to the Visual tab on the properties and set its purpose to proxy. Then, return to the main assembly and make sure to remove the previous collision presets added to the rollers, and you're all set. Finally, to achieve the best performance when simulating a robot, the optimal process is to have each rigid body having a single mesh and a set of colliders inside of it. To do that, start by saving a copy of your robot asset and remove anything that is not the rigid body that you want to optimize. Drag the rigid body out of the root prim and open the Mesh Merge tool to group all meshes into a single component. For assets imported with the Onshape importer or the CAD importer, select the Override Looks directory and provide the path where the materials are assigned on the stage, and then click on Merge. To check the mesh properties, open the Physics Inspector and select the main body before being merged while the simulation is running. Finally, add the Mesh API to the root prim and Collision API to the collision objects that you will include in your asset. Now, go back to the original robot USD and delete the prims inside the rigid body, and click on Add Reference and select the USD just created.
Next, let's talk about how we might edit the scene once we have a robot imported. Now that we have the Kaya robot imported, the first thing you probably want to do is to move it. We have an example connecting up the Kaya to a joystick. You can find that in Isaac examples, controlling input devices, and Kaya joystick. I have an Xbox gamepad with me and plugged in, so once it's all loaded, you can see that I can move the robot about. If you want to see how the connection is done, you can open up the Python script corresponding to this example by clicking on the button on the right hand corner, and this is the script that corresponds to the Kaya example, and everything from loading the environment and hooking up to controllers are all done here. The nice thing about this Python interface is that it's hot loaded, which means if I make a change in the script and save it, it is automatically reloaded and implemented. So let's change the background to something else and save it. And we'll reopen the example again, reload the scene, and you can see now that the background is a different one. This makes debugging and iteration much quicker. We can also edit our scene right here in the GUI. Let's add an obstacle on the table for the Kaya to run around. We'll create a cone and fix it to the table. So when you first add a mesh, it actually has no physical or collision properties, so Kaya can just run straight through it. In order for it to actually be an obstacle, we will impose a collision property onto the mesh, and now the Kaya actually collides with it. We can also do this in this semi-ad hoc way through Python scripting using the script editor in the GUI. So let's open up the Python script editor panel. I have a script that lets me create a bunch of cubes and spheres in bulk. So a bunch of objects are added to the scene in one go. And let's make them different colors. And we'll go and create a different color, a different material with different colors, and assign them to the cubes, the spheres, and the obstacle. So even though the composition of scene was done using different methods at different times, but you can see that if I drive Kaya off the table and I reset, all the new things that are added are still there in the scene, and they are reset as well. If you save this whole stage as a USD file, then the next time you open the USD, you'll have all the obstacles and the cubes and spheres in it to start. Next, let's talk about what we can do in Isaacson. Isaacson offers a range of synthetic sensors, such as cameras, depth, point clouds, LiDAR, ultrasound, as well as IMUs and context sensors. We also provide ground truth for some of the baseline perception, such as semantic labeling, segmentation, and bounding boxes. So now let's jump in and see how to attach some of these sensors to our robot. Let's first attach a camera. There are several ways to pinpoint camera locations. One way we can do this is finding a viewpoint that we like and create a camera from that point of view directly. We can open up multiple viewports to see all of our cameras at the same time. We can also attach the camera to the robot's base link. So now when the robot moves, the camera moves with it. And this is how you might simulate an onboard camera. Along with the camera sensor also comes with depth sensing. And you can see that by opening up the synthetic data sensor visualizer at the top of the viewport. We can also choose to receive other perceptual informations like segmentation, bounding boxes, and etc. But you have to label the scenes first in order to see some of these. There is an excellent series of video tutorials made by my colleague Shubik that goes over how to label your scene and get segmentation data. So I won't go over that here, but those can be found in our documentation website. I'll just quickly do that so you can see what it looks like with the scene that's labeled and segmented. What you see here is just a snapshot. If you want a time series, then you'll need to check out the synthetic data recorder. Again, this was covered by Shubik in his tutorial as well, so make sure to check out that if you're interested. Let's add some other sensors. Kaya doesn't have a LiDAR sensor, but let's just add one for fun. We'll attach it to the top of the robot, and we'll make it 3D, and we'll choose to visualize the LiDAR rays. We'll reduce the scanning rate to something less seizure-inducing. And now when you play, you can see the LiDAR spinning and the rays turn red when it hits an object. LiDAR and ultrasound are sensors that you can add both using the GUI as well as using Python scripts. But we also have some sensors that are only available through Python right now, such as IMU and contact force sensor. Here I've copy-pasted a script that lets me add an IMU sensor to the robot and then plot the acceleration out onto the screen as bar plots. So now when I run it and the robot is accelerating and decelerating, you can see the bar plots moving accordingly. The simulator will most likely to only be a part of a much bigger system. So we've built in communication bridges to ROS1, ROS2, and Isaac SDK. My colleague Hamad will join me now to tell you more about the details of our ROS support.
There are two different ways you can interact with Isaacson and ROS. The first, shown on the left, is where you can start Isaacson as an interactive UI application. Here you can create ROS components via the UI, add them to your scene, connect them to sensors, and then press the play button to publish their data. Specifically, here we're adding a ROS camel publisher and a TF publisher to publish the post tree and show the resultant image inside of Arvis. So hit play, and then you can see the images there. Now on the right side, we have a native Python script that shows how you can launch the simulator, create the camera in the scene, create the ROS camera publisher, create the ROS poster publisher, and then finally start the loop to run the application and publish the data. In both of these cases, the simulator connects to ROS core as soon as it becomes available. And in the case of ROS2, everything remains the same in the scene, but you just switch the backend in terms of which ROS bridge you're using. Now, Isaacson comes with several built-in components for publishing camera, LiDAR, post tree, the ROS clock, joint states, etc., which go through the ROS and ROS2 C++ APIs to provide better performance for publishing, especially for things like camera images, data that requires higher bandwidth. But because everything in Isaacson uses Python as its scripting interfaces, both ROSPy and RCLPy for ROS2 are directly available. The benefit of this is that all standard ROS messages are available to you, and because every single sensor interface provides Python bindings, you can access the data directly, and you can create your own ROS publishers in Python to publish any sort of custom mix of data that you'd like from the simulator. And you can subscribe to your own messages, publish messages if you want to control your robot, and so on. Next, we're going to go into 3 different workflows that are made possible in Isaacson using the ROS bridge. The first shows how you can use an existing motion planner, such as MoveIt, to control a manipulator with Isaacson. So here you see a simple room environment that is shipped with Isaacson and the Franca Panda robot. On the simulator side on top, we have a joint state publisher subscriber, a ROS clock to make sure that the sim time is published, as well as a post tree publisher to make sure that the TF for the entire robot is being published. And on the bottom, we have Arvis running the MoveIt planning stack, and we're showing how you can easily specify a plan for the robot arm, execute it, and the robot simulates in Isaacson, and as well as the opening and closing the gripper to perform any such actions. Now from here, you can imagine that you can increase the complexity of the scene. You can add other rigid bodies. Let's say I wanted to add some blocks that the robot would then grab. You could publish the post tree information for these extra rigid bodies and then use them to build a more complex manipulation task. Now, one thing I wanted to highlight, and it's pretty subtle, and that is because everything here is real-time ray traced. If you notice, the room has one large light on the ceiling and one large light kind of coming from the window to the front of the robot that you cannot see. And even though you cannot see these 2 light sources, they properly reflect off of the plastic material that is being used on the robot. There is no special kind of setup from the user required. Everything is just automatically taken care of because the scene is being ray traced. Next, I wanted to go into the second workflow, which involves using the ROS2 navigation stack to simulate multiple wheeled robots in an indoor environment. In this case, we're going to be using a new environment coming with Isaacson in the upcoming release, which is a hospital environment, along with these simple differential bases, which have a camera on the front and a LiDAR on top. Now, before we can use the roster navigation stack, we need to generate an occupancy map for our space. Now, for simplicity here, I'm using the warehouse environment that comes with Isaacson and showing that you can select the objects of interest to define a 2D area. You can then specify a Z min and max height to kind of have a volume of area that you want to map. And this is really important in cases where you have shelves, because if you have a gap in the shelf, you don't necessarily want that gap to mean that there is also a gap in the map. You could specify a larger Z volume to set the area as occupied. Once you have decided on the area that you want, you can select the entire space, click Calculate, click Visualize Image, and then after that, in the window that pops up, you can rotate the image to whatever orientation that you require for the navigation stack, as well as directly copy and paste the YAML file for the navigation config. And once you have that map, you can hook it up to the navigation stack. So here, we specify the map in the config. We then launch 3 separate ROS2 nav instances, each with its own namespace so that it understands which robot it's communicating with. And within RViz, we can start up each of the navigation stacks, provide a goal for the navigation, and then you see the robot starts driving towards it. Now, the data being published from each of the robots is 1 depth and 1 RGB image, as well as a single 2D LiDAR for each robot. And that 2D LiDAR is what is used for navigation. Hardware-wise, we're running all this on a single RTX GPU and a 12-core CPU. And just to give you kind of some rough numbers where we are currently with the release of Isaacson is that each of these robots is being simulated at 30 FPS. And we're hoping to improve that with some more optimizations. But even on a single machine, you can simulate multiple robots with multiple navigation stacks running. And the bottleneck here starts to become both the GPU in terms of just how much you're rendering because of those 3 cameras, as well as on the CPU side, each ROS nav stack, each roster nav stack is pretty heavy. Then finally, the third workflow involves doing synthetic data generation with domain randomization and publishing that data directly to ROS. So before I go into the actual application, I wanted to talk about some of the different randomization primitives we have available in Isaacson. So there's a lot happening in this video, but to just break it down a little bit, on the left side, we have 4 different spheres with different materials. And all we're doing here is we're hiding and unhiding them randomly. So we're changing their visibility dynamically. In the center, we have a torus whose material is being randomized. So you can see different reflectivity, specularity, metallic, kind of all just changing every, I think every quarter second. On the right side, we have a cube whose texture is being changed. We have a background environment map and this blue plane that are being rotated along the z-axis randomly to kind of give you more background randomization. We have a cone with a light on it, and that cone, even though it is being randomized in terms of its position, its orientation always faces the torus. And then the light itself, it's if you look at kind of the specular reflection off of the plane, you can see that its color is being randomized. And then finally in the center we have a cylinder whose position, orientation, and scale are all being randomly changed every second or so. Now using all this, you can do some interesting things. So here we have that same warehouse environment that you briefly saw earlier in the occupancy map generation. But we can randomize its shelf positions, the background lighting, and some of the textures. Now you can imagine that for a scenario where you wanted to do object detection, you could easily dump these images to disk with all the labels using Python. But with ROS, we have some more kind of interesting applications that we can enable, where now we're doing a live simulation where in the bottom you can see that depth and RGB are being published, as well as a full 3D LiDAR scan. And as the robot is driving forwards, we're perturbing the entire environment randomly every second or so. So if you had an existing stack in ROS for capturing data using real cameras, you could use, without hopefully too many changes, the same stack and publish the same information that you had in the real world from the simulator, and see how things like, if you're using that to train a network, how that network behaves during inferencing to random perturbations, or things like that. Even though this is a bit of a contrived example with a lot of randomization, you can imagine that you can kind of do more subtle changes to see how that affects your robot's algorithms.
I just want to quickly mention that there is a talk and a blog that details a end-to-end sim-to-real example of training a JetBot to autonomously run on a Lego racetrack. This is starting the training on the simulator and transferring the output to a real robot. That was done by our colleagues Locke and Gus. And the blog and the talk goes over step-by-step on how to use a synthetic data generator and the domain randomization tools, as well as how to script your training algorithms with the frame-by-frame outputs from the simulator. So that's all we have for you today. Here are some basic information regarding what you need to run Isaacson. The same information is also on our docs. And here are the links to our documentation, as well as our installation guide, and also a forum where you can ask questions, and either someone from our team or someone from the community will help with answering your questions. And that's all. Thank you very much.